Hello guys, welcome back to the Data Structures and Algorithm course brought to you by Asha Akanksha Foundation. So we will be starting a new topic linked list in this lecture. So let's start. So the first introductory session to linked list would be what are the problems with arrays. So uh, I guess you have looked at the previous lecture on sorting. So from that you can easily say that if the arrays are sorted, it takes order of log n time to search for an element, isn't it? So that is from binary search. And insertions into arrays may take large number of operation as it may involve creating a slot and shifting the number of elements in the right of it. And deletion from the array also may take large number of operations because you have to shift the elements to the left. And the time complexity of insertions and deletions in arrays is order of n because it is the worst case time complexity. And array size has to be fixed in the beginning, so this is a very major issue that we have to deal with the array. So there is a need to have another data structure which uh, can improve this issues. So we come up with a data structure that is list. There is array list in Java and vector in C++. So you can consider a list of integers like 16 and they're like this list, this one, and it can be thought of as an element 16 followed by another list. The second list can also be thought of the element 8 followed by 8 list. So basically what we are doing is numbers in adding numbers in the front of the list. Thus any list can be thought of as an element followed by a list. So we can come up with a recursive definition of a linked list where each element is linked to the next one. So here's where linked list concept is started, and now we'll see how we'll implement the linked list. So a linked list is a linear. So first of all, let's know what is a linked list. A linked list is a linear data structure which each element is separate object. So in the linked list, it is only linear. Like I guess must have learned about trees. Like they have uh, um, they have quadratic, or you can say they have binary. They are binary data structure because they have two pointers like right, left, and all that thing. But in the linked list, you have only one pointer that is to the next one. So that's why it is a linear data structure, and where each element is a separate object. Each element of such a list needs to comprise of two items, the data and the reference to the next node, as I said earlier. The object that holds the data and refers to the next element in the list is called a node. This is basically a wrapper class which contains all the elements like the data and the reference to the next node. Data component may actually consist of several fields. For example, in a linked list of students, the data could be student's name, roll number. Yeah, so data can be manipulated accordingly to our needs, and there is nothing to worry about that. But the necessary condition is that you must have a next pointer for the reference of the next node in the linked list wrapper class, that is node. So let's see how we store a list in an array, like an array. So in deep down the computer, all the elements or all the data structures are stored in a memory address. Let's say this is the memory address of the array 0th index, and the list content is 36. So it's you can say for these memory address we have for this array indices we have these contents. So linked list, let's build a new thematic approach, or you can say thematic concept of what a linked list is. So as you can see, these are the individual objects which are linked to each other by a reference pointer, which is this. Like I said, the node class has reference pointer to the next node of the linked list. These arrow represent this only, and it also contains some data, and this 42 is the data in that node. So a linked list is a series of connected nodes. Each node contains at least a piece of data. It can be of any type, and the link to the next node of the list. Head points to the first node. So you must have a head pointer for a linked list to be traversed. So links are generated by system and the last node pointer is null. So it means that the linked list has been traversed completely and now it's finished. So let's see how linked lists are stored in memory. So linked list in, in the previous slide we have shown how arrays are stored in the memory address. So as you can see, arrays require contiguous memory space, like that is 3200, and the next memory address it requires is 3202, then 3204, and like this. You can't store arrays array contents, like if you have, so the you can't store it in discrete manner. So this is a very big problem. Like if you do not have such if you for a very big array you do not have such contiguous memory space in your memory, so you can't store them discrete in discrete memory addresses. So that's where linked list plays a key role in that. In linked list you can store the content in discrete memory address, like in you can store one node in this memory address, another node at this memory address, and one thing you know about is like the reference pointer to the next memory address of the next node. So for this for memory for node at 2020 you got the next pointer at 450, and for 450 had the reference pointer of the next node at 3600. So like this you can store any node at any any free memory space. So this is a very important and revolutionary concept of linked list. So you must remember this, that it does not require contiguous memory space. So let's look at the how we define list node. So list node can be just defined as a wrapper class in which we have data of the linked list and reference pointer that is of type node linked to the, and this is a link to the next node. So yes, this is the constructor of the node. I guess you are able to understand this. So we can extend the definition of node also, like we can override few constructors of the node. This is a simple node. If we don't pass anything, this is constructed. If we pass a data to the node, we'll get a node with a data but with no link to the next node. If we pass both data and the link to the next node, this will be the constructor used. So like in this we have first node, this is the head pointer, we give it the link to the next linked list, next node, this is the data of this node, that is 44, and this is the link to the next node, and we go on like that. So now we will see how to insert a node in a linked list. So the linked list is initially empty, the new node becomes the front node. Otherwise, we will have to link the previous front with the new node and declare front to be the inserted node. So how we'll do that? So suppose we wanted to insert a node containing value 82 at the front of the linked list. So our front will be 50 and its next pointer will be, assume this is the linked list. So we have 50, 33, 60 with each links. So we'll first form a new node with the value 82 because we have to insert 82 in this linked list. So we'll first make a node with value 82 and the reference pointer as null, and then we will link the reference pointer of the node 82 to the front. So finally we declare node 82 to be the new front node. So the code would look like something this. We'll first initialize the new node by putting the value as 82 and the reference pointer is null. So we will check if front is equals to null, then the new node will be the only node in the linked list. So front will be equal to this new node. Otherwise, we have to set the link of the front to the new node, and now we'll make front is the new front of the linked list. So the linked list was look something like this now. So you can take a look over here. So let's take some another scenario that we wanted to insert a node containing value 82 at the end of the list. Uh, so in this case, we will want to insert the node 82 at after this 16th node. So first we will form a new node with value 82 and reference pointing to null. Next, we have to traverse till the last node of the linked list, and then we will set the next reference pointer of the 16 to the new node which has been created of value 82. And the code for this looks something like this. So we'll create a new node with a value 82. We will traverse the this is how we traverse a linked list. We'll traverse the linked list till the last element, and then we'll set the link of the last element to the new form node. So now we'll see how we traverse the list with a pointer. So if we are given the front pointer, we will first check if the next of the current pointer is not equals to null. So if it is equals to null, we will not print anything. If it is not equals to null, we will print the data of the next node, that is 50. And then we will do the same thing for the 50. We'll check if there is next node present. If there is a next node present, we'll print the data. Otherwise, we will not print anything and will return from the while loop. So the new linked list will take form something like this. We have the previous linked list as it is, and now we have the 82 as joined after the last linked list. So what if we insert a new node in the empty list? Then the code needs modification. If front was pointing to null, then we set front to the new formed node, as the new linked list will only contains this node. So we have seen the code for inserting a new node at rear in any list. We'll now move forward. So we'll now see how to print and count nodes of a list. So let's see how we'll print contents of a node. We have talked about this in brief previously, but we'll see the exact code we will use to print all the contents of the node. So we'll set a pointer to the front. I will traverse through the list and print contents of each node as long as link is not null. So we'll create a pointer front. We traverse to the front till the pointer is not equals to null, and if it got null, we'll move out of this while loop. So we'll directly print the data of the current pointer, and we'll move the current pointer to its next reference. Recursion and linked list. So recursion in linked list we very often use recursion concept. So we employ recursive methods to operate on linked lists. This is very natural as linked lists themselves are recursive data structures. Recursive methods operating on linked lists are often simpler to write and easier to understand than their iterative counterparts. But iterative counterparts are much more recursive methods take extra method overload in the compiler, but the iterative counterparts are much more efficient than the recursive ones, but recursive methods are very simpler to write. So later when we study tree data structure, we shall see that some methods can only be written by using recursion. As we have discussed in the recursion lecture, that not all the recursion function can be written iteratively. So this is the recursive method of printing the content of node. We'll set a running pointer to front and we'll print the data for this node and then recursively call the function with the link to current pointer line. This is the function we have defined for the print list. In this, the parameter is a pointer. So if pointer is null, we'll just return, and if it is not equals to null, we'll print the data and we'll recursively call the function for the link to the current pointer. And similarly, we'll see how the recursive method of count number of nodes look like. So we'll set a running pointer to front. we will start a counter, will traverse through the list and increment the counter as long as it is not equals to null. So this is the iterative method of this program. We'll see how it will implement it recursively. We'll just make a function count list with a parameter pointer, and if pointer is equals to null, we'll just return 0. Otherwise, we'll add 1 to the 1 to the count list, 1, and the function with the parameter to the link to the current pointer. So this will give us the total number of nodes. So now we'll see how to insert a node at a specific position in the list. Assume that node 50 is at position 1. Suppose we wanted to insert a node containing value 82 at position 3. So we'll assume that 50 is at position 1, so 33 will be at position 2, 16 will be at position 3. That means after node we have to add a node after 33 and before 16. So this involves breaking the list and setting toLink into new values. So we'll first form a new node with value 82. We'll reach the position 2, that is 33. We'll get the link of 33 and we'll use it to set a link to 82 so that 82 and 16 also get linked. Next we'll set link of 32 to address of new node 82. So we'll see it an animation that we have first reached this 33 node. We'll then set the we'll then break this link to the 16, and we'll form a link between the new form node, that is 82 to 16, and then we'll make a link from the 33 to this new form node. So as you can see, first we'll copy the link from the node that's directly already the link, that is 16, and we'll change the link in the node that's already in the list. So this is how its code will look like. So we have assumed that position of first node is 1. So this is the function for insert at position. This is the value we want to insert, and this is the position at which we want to insert. So we'll first form a new node in this line, and we'll set this as a front pointer. We will initialize a position variable. So we will traverse through this array. We will traverse through the linked list till we get to the position. If the current position, if the current if the I is equal to the current equal to the position we want to insert, we will we will store the link of the current pointer to the new node temp, and then we will set the link to a link of the current pointer to the new form node, that is which we want to insert, and we'll set the link of the new form node to the temp in which we have stored the link of the current pointer. So and then we'll break from this for loop because we have done our task, and then we'll just return the new form link. So let's see how we'll delete items in linked list. To delete the first element, we'll change the link in the header. So we will change the front pointer to the next of the current pointer. So deleting the last nodes, these are the steps which we have to follow in order to delete the last node. So we have to set pointer previous, that is previous node, to first node of the list, and then we will set pointer current to the second node of the list. We'll traverse the list till current reaches the last node, and we'll set the link for previous to null so that last node is not reachable. So this is previous, which is initialized as the front pointer, and this is current, which is the next to the front pointer. So till the next pointer, till the next pointer link of the current pointer is not equal to null, we'll traverse the link, and we'll at last we will set the link of the previous node to null. So now we'll see how to traverse a list with 2 pointers. So this is the animated version of this code. So we have initialized the previous pointer as the front pointer and current pointer as the next of the previous pointer. So that's how previous and current will look like while traversing the linked list. Now when the current pointer reaches the last node, so it will set the link of the last node to null so that the last node is not reachable. So let's see how can we delete a node containing data D. It is very similar to what we have done previously, but it will stop whenever we found the it will only stop whenever we found the link we found the node with the given data. So this is how its code will look like. I will not discuss it elaborately much because we have discussed similar kind of concept in previous slides. So if you want to look at it, you can pause the video here and take a look at this. This is the animated version of that code. Now we'll see a very important question that arises, that how to reverse a linked list. This is very frequently asked in interview questions also, so we'll see how its algorithm looks like. So we will create another list with the reversed contents of the current linked list. So we'll read contents from list A and add them to front of list B. So this is a very easy approach actually. We'll see how we can optimize it, because in this particular scenario we are using order of n extra memory space or auxiliary space. So we'll just traverse the list of A, and we'll add the element in the B in the first position. So that's how it will look like, the new node B which is got reversed. This is how its code would look like. So the optimized version, that is reverse linked in place, what it means is without using any extra memory space. So for that we'll need to use 3 pointers, that is previous, current and next. We'll start with pointing current to the first node. We'll initialize the current to the first node and previous to the null, and next is also to the null. So we'll traverse the list in a while loop, that is in iterative manner, and we'll set the next of the current we'll set next to the link of the current node, and we'll set the link to the and then we'll set the link to the current node to the address of the previous node, so that it reverses, and then we will set the previous to the current, so that the process moves further, and then we'll set current to the next, so that we can iterate for the next elements. So we'll do this in a while loop, while current will not be equal to null. So when loop is over, we'll return the previous node, because at the end current would be equal to null and previous would be the last element that we have traversed, and it will give us and this will become the new head pointer of the reverse linked list. So its code will look something like this. We'll initialize previous as null, next as also equals to null, and current is the head of the current linked list. So we will traverse the linked list in a while loop. So we will do it while current is not equals to null. We will store the link of the current pointer in the next variable, and we'll then set the link of the current pointer to the previous node, and then we will move previous to the current node and current to the next node. In the next node we have stored the previous link of the current. So basically we are moving back from the start to the end, but while setting the links in the opposite manner. So at the last we will be left with the previous node, because current will be equal to null. That's why we have came out of the while loop. And at the last we will the first pointer of the reverse linked list would be stored in the previous. This is the recursive function of the same reverse linked list. So you can take a look at this. This is very similar to the iterative method, but I will prefer the iterative because recursion needs extra function call overhead. You can pause the video and look at this code. So in the next video we will look at the circular and doubly linked list, and if you have any questions regarding this video or any conceptual right arise in this video, you can comment down below, or you can also reach out to us at our Insta and Facebook pages. Hope to see you in the next lecture. Till then, stay safe, happy learning. Thank you.